go ahead and get started. Okay, so we kind of left off with this climate change and the influence, and we started talking about possible ways to fix eutrophication and things like that. So I guess part of the reason to bring a laptop was to possibly search some articles. And so I guess as part of the rest of this course, I would like for y'all to find an article that interests you. It could be like, it could be something that was part of your presentation. So like green roofs, like I'd love to see an article about green roofs. Or it could be anything, but something that we can maybe discuss as a class about potential solutions. So like potential solutions to hypoxia zones, or potential solutions for subsidence, or anything like that. So if you give me the article, like we can start to formulate a discussion about some things that might interest you, because what I think might be cool to discuss, y'all might not. I guess I'll make an assignment part of that where you get an article, bring it to me, and then we'll try and discuss some of that stuff about it. You know how to search for articles on Google Scholar, not on Wikipedia. I use Wikipedia so that I can get to my Google Scholar sometimes. But yeah, so we'll work on trying to find an article so that we can discuss that. Like Brent and I were having a discussion about what happens to the nitrogen in the hypoxia zone. What are some potential options that we can do? How do we fix that, or try to add more dissolved oxygen back to those systems? Or how do you fix eutrophication? What about acid mine waste drainage? You know, how do you get the soil to flocculate out of a stream so that it's clear now? And they actually do that type of stuff. I guess as part of when I was working with the American Society of Mining and Reclamation, like those were the things. Maybe it is phytoremediation. It could be something. It could be anything. The whole goal is to get you thinking about this article and how to go about this solving that. Maybe we can discuss that in class. What else? I believe that I'm going to offer fertility in the fall. If you are interested in taking or retaking that. But we're trying to get the petition together. So I don't know if that's in someone's curriculum that maybe you do want to take fertility, but I should at least let you know that is possibly going to be a class in the fall. The more people that we get that want to take that, the more likely it is that we're going to offer it. So we have like at least 4 or 5 students who have raised their hand and asked me if I'm teaching fertility in the fall. If that's something that interests you, let your advisor know. Ms. Tanya's going to send out an email about the potential for that, start a petition. Okay? What else? I think we are having a environmental conservation organization meeting next Thursday. I'll have to look as well. I'll get a flyer together for that, and maybe we can discuss some of those things in class too. So we left off with what are some potential things that we can do, and with this climate change thing, can we reverse climate change? Yes? How many people think yes? No? Everyone else is kind of, wait, if you weren't yes, then you're kind of on the no. What about slowing it down? Some people believe that there are some things that we can do that can slow down this. We can at least not speed it up. Maybe that's a better way to put that. Like we don't have to contribute to the problem, and the less we contribute, then the less the problem is. Much like our nutrient loads in the river, right? So like those are some things I'd love to just sit down and discuss as a class. Like how do we go about that? That's where the articles come in, right? Maybe that makes it a little better. How do we go about fixing eutrophication? What are some potential options? How do we take nitrates out of the water? I had to do a presentation on like a bioreactor that was basically this ditch that they put a whole bunch of wood chips in, and the microbes completed the denitrification process. And they kept it anaerobic, so they didn't introduce any water, so that the denitrification process continued, and now we have the release of nitrogen back to the atmosphere, and the water that goes into the river doesn't have as much nitrogen in it. But we can't do a bioreactor, we just go out there and dump a bunch of wood chips in the hypoxia zone, right? So there's a whole bunch of things to think about when we are considering how do we fix this. One way that we discussed at the last time was having an accounting of this ag water. So kind of like our, I was talking about soil chemistry class, kind of like this paycheck budget. So we need to know what we have on our land and how to calculate the amount of water that's falling on our green roof or on our rooftop, and we're going to collect this water. And I've got some examples with some math in them that everybody loves to do. So we talked about a watershed. I think this is where we left off, was this whole watershed. That is this area that is all the water flows through one outlet, possibly here, or maybe it flows right here, depending on the elevation of that watershed, right? So watersheds are kind of like this big bowl. And then there are bigger bowls that this one bowl fits in. And all these watersheds are connected. So here is, where are we? Here is our Caney Fork, and all of these are all part of a bigger system outlined that are all part of a bigger system. So some of y'all might have seen this. We are pretty much in this Mississippi River Basin, which is everything to the east of the Rocky Mountains. So all of that stuff flows out through the end of the Mississippi River. So everything in this entire bowl eventually gets flushed out the mouth of the Mississippi. So all the nutrients, all the soil, all the junk. Anybody live near the Mississippi River? Nasty, isn't it? Not, you don't want to, I'm not, because all of that stuff is finally making its way down to the coast, which is where I'm from. So each one of those basins are part of that. They all have different names, so it looks like we are in the Tennessee basin. And then finally that all flows out to the end of the hypoxia zone, out the mouth of the Mississippi, and all the junk that is with it causes this problem. Since we can't necessarily fix this, the only thing we can do is prevent it from getting worse. Right? That's the plight that we're stuck with. How do we go about fixing this? There are plenty of people in Washington that are trying to figure that out. They haven't come to it yet. So the kind of the thing about watersheds is that we were going to try and find this, the highest points of the watershed, and the water flows downhill, but it also flows perpendicular to the contour lines. And so when we were doing our web soil survey exercise, some of you had never seen a contour map before. Some people had. And so each one of these lines represents a distance and a slope. So the distance between those lines being, let's say, 20 feet. And so the closer that the lines are together, the steeper the elevation. See, makes sense? You got the blinks going. All right. So, not that you might ever need to read one, but at least if someone pulls one out, you can say, I've seen that before. And you kind of have an understanding there's a distance between those lines, and that gives us the slope of a particular terrain. We had to read these in the Army in the 90s. And that was tough, in the middle of the dark, with a flashlight and a compass. We don't have to do that anymore. So the way that we're going to mark these watersheds is we're going to find the highest point. So we talked about this being a spot elevation, and we know that that's about 350 feet. This next line would be 370 feet. So we know that the top, we have a top there, There's another top here, 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 are points of highest elevation. And so everything flows out the mouth of that watershed. Is this something y'all have done before, Michaela? Like this looks familiar? This looks familiar from Spatial Tech, or where did you do this at, Alicia?
Like 10 different classes, I don't know.
Okay.
It's not foreign.
Anybody else seen a topographic map? Hannah, you good? Right. So sometimes you might need these and sometimes you might not. But being introduced to it and understanding that the way we're gonna define those watersheds is by the highest points of elevation, and it forms a bowl, because they're all moving into the center and then flowing out the end. So the kind of the primary thought process of this hydrologic theory is to get the precipitation back into the stream, because that completes the water cycle, right? Like, it would be great if, I don't know that it would be great if, because we need the water in order for our plants to survive, but to complete the water cycle, there wouldn't be any loss to the soil. We would expect our cloud with our rain to go back into the stream. That would be the most efficient completion of the water cycle, right? We don't have any losses. It just constantly in the stream, lake, river, pond, ocean, evaporates back into the clouds, falls on the ground, runs off. But we have plants that need that water. We also have soil that is going to adsorb some of that water or infiltrate. So there's going to be a loss there. The thing is to figure out where those losses happen. And when we can account for a loss, I actually had to do this with my bank account, because I was like, how come I ain't got no money? Printed out all the transactions, highlighted where I was stopping at the grocery store, eating out. So I got $200 in eating out. That's how come you're broke. Same principle. You gotta figure out where the losses are coming so that our budgets can become more efficient. So our effective precipitation is this system. Whatever falls and runs off, which their runoff will happen, the water will move to the lowest point. And then there's the abstraction, the stuff that gets caught by the trees and then adsorbed into the soil that infiltrates. It might get evaporation, evapotranspiration in the soil through the plant, back into the atmosphere. It's a good idea to have an understanding of how the precipitation forms, and as I was putting this slide together, like even years later, the light bulbs are still going on. Alright, so we're all familiar with, or most of us are familiar with the fact that there's no rain on the other side of the mountain, right? Anybody from the West Coast? No? Anybody ever been to Portland, Seattle? It rains a lot there, right? Well, mainly because the air is getting lifted as it's coming off the Pacific Ocean. I'll try not to turn this into a meteorology class, but it's important to kind of understand how this precipitation happens. So everything on the west side of Colorado gets the rain. Everything on the east side of Colorado doesn't. So then next, we have this convective. And so, I guess I do need to turn this into somewhat of a weather class. Do y'all know why wind blows? Can anyone explain?
It's air moving from a high pressure area to a lower pressure area.
Correct. So he said it's air moving from a high pressure area or from a low pressure area. High pressure area to a low pressure area. So that's like diffusion. Because there's no pressure over there, the air has to go somewhere. So we get this movement of air based on pressure, right? In a heated surface, in this convection, what we have is we have this big circulation. So like an urban heat island. And this is where a green roof would come in because it's taking in some of that heat, and that's not causing the air to rise. So hot air rises, cold air doesn't, so if you get this temperature that pushes down, that air starts to rise. So we have this movement of air up. So next, because this is an area of high pressure, it moves to an area of low pressure. Low pressure to high pressure. Next, we have this convergence of this movement. When the air goes up, it has to be replaced with more air, right? So in a field, you might have the air moving towards this area of low pressure, converging and then going up. So convergence. When two things collide, something happens. An immovable object meets an unstoppable force, there's going to be something. So those two drafts of air meet each other that have moisture in them. And when they do, they go up. And so that's how come there won't be any rain in the forecast, but all of a sudden about 3 o'clock in the afternoon, here comes a rain shower, and you go, I didn't bring my umbrella, and I didn't expect this while I was working in the field, and now my day's ruined. Some of us have been there. It's about to rain now, and didn't see this on the forecast, I planned for this day, and then boom. So this is what happens. Eventually enough air rises into the atmosphere that has that moisture, and we get a rain shower. And then we have these fronts, where we have a warm front pushing up a cold front, or a cold front pushing up a warm front, and causes that very bad weather, because we have a hot air mass meeting a cold air mass, and there has to be some transfer of energy there. And when that energy transfers, the rain comes down really fast, because now we have all the moisture from the hot air and the cold air. That makes a whole lot of moisture, and it has to go somewhere immediately, right? So, having an understanding maybe that your precipitation is happening this way from convection, which is always happening. We have this convergence, so if we can slow the air movement down, we might be able to slow some of our precipitation down. But then it's up. We have one that comes around, and then we have one that goes back up through the middle. So these two are happening in our fields all the time. That's how come we get a rain shower. When we unexpectedly. Not that we need to write a whole bunch of stuff down on this slide, but just to understand kind of the principles of why we are managing our watersheds. Mostly because they enhance those watershed functions that influence plants, animals, and humans within that watershed. Because we all live inside this bowl. What is the impact of one of our activities, or the rain, on our life in this bowl? And so that's where it's going to come into water supply. Someone did something on water rights and water privatization, how we use our water, our drainage and our stormwater runoff. Those are good jobs. If you know how to manage a watershed, yeah, that's a good job. I took a watershed class in my PhD, and I was like, man, this would be really cool to have this job. Most of it's done by computers. You just enter numbers into an Excel spreadsheet, and it spits back out this value, and that's the one you use. And there's just a whole bunch of stuff that goes into it. Some of the places that you can get some of these data resources for this information, we've heard of many of these, but our environmental data comes from NOAA. So they have all this information. We'll end up doing an exercise where we download that information from NOAA, put it into an Excel spreadsheet, calculate precipitation, evaporation, things like that. Like, I didn't think I was going to use this in my I thought I'd never use it again. And I had failed to measure the amount of water that was evaporating out of my containers. Big mistake. So I actually had to go back and back calculate what the evaporation out of my containers was, and then recalculate what the concentration would have been if I had put the water back. And I promise, I never thought I was gonna use this stuff again. But sure enough, here came this opportunity, and when it happened, I knew exactly what to do from taking that watershed class. It was super cool, I was real proud. No one else cared. My boss was like, yeah, that's great, you made a mistake. But I fixed it. So, if you didn't make the mistake, you wouldn't have had to fix it. All this schooling y'all are putting me through, and I finally use it, and then you're down on me, so. National Weather Service will tell you about rainfall depths and intensities. USGS has a lot of information, a lot of cool tools that you can use. He's shaking his head in the back. Like, that's where you find out like stormwater discharge, peak flows, stream flows, things like that for stormwater management if you go into that field. And then within each one of these services, you can look through a number of different things. And then like the U.S. Army Corps of Engineers, these are really good jobs to have. They pretty much tell you what you can and can't do, and there's nothing you can say about it. If they say no, you say, okay, thank you. And if they say yes, you say, okay, thank you. So, this might be more of like environmental engineering over in Prescott. If there's anybody in here that is over there, she's stomach just turned. Have you taken classes over there? No. Whole different from what we're doing here. They're the ones that do all those physics and calculus calculations and engineering type stuff. For this class, we're just gonna calculate how much water is gonna fall over our farm and what happened to it. All right, because that's gonna be most pertinent to us, or maybe over our green roof. I really like that concept, and I put one in here for us. How we would use this, engineers use that for all kinds of different stuff, but for us, we want to make sure that we understand the consistency of our precipitation and the cycles of what's happening to that when it rains. Yay, math. Now I promise you, I make this math very simple. We're only gonna do like multiplication and division. And so, do I need to go over this very much? We all remember these calculations from one of Dr. Earhart's classes. All right, so in this problem, we are going to calculate the rainfall in a rain gauge that has about a 2.5 inch diameter. And the depth in the rain gauge was 4 inches. I wish I had my ruler. I have a ruler. That actually works out pretty well. So, you just have a bucket. Your rain gauge can literally be a bucket. It does not have to be something fancy. But probably a cylinder that's kind of up off the ground a little bit. And so we had this rain gauge and to a depth of 4 inches. Right? How much water fell? So that's what we're calculating here. We typically tend to work in SI units just because they have a better system than we do. Because once you get into centimeters and millimeters and meters, and it's just factors of 10. Rather than how many ounces are in a pint, and pints in a gallon, and gallons in it can get. For some reason, our system doesn't work very well that way. So, we will calculate, we'll convert everything into centimeters, and then now we can conduct our calculation. So remember that we have a cylinder, and then a radius is half of the diameter. And so y'all calculate the amount of rainfall, the volume, in our rain gauge. Pi r squared. Okay. Put that sheet up first. And where this will come into play is if you have an evaporation pan. Anyone dealt with an evaporation pan? No? I think I might try and implement that in future classes, how to set one of those up. Your evaporation pan, no? So we've converted to centimeters. We're gonna do pi r squared. Remember the radius is half of the diameter, so that is 6.35 divided by 2. And then square that. And then multiply times the depth. You know what you got, Josh? Okay. Everyone else get it? You're just nodding, so we're gonna be doing that all period, so class. Period's high school. So we have a rain gauge of 6 inches, and the depth of the water is 2. When we convert it to centimeters by the pi r squared, our volume of rainfall is 926 cubic centimeters. So you build a green roof, how much, so from here we're gonna collect how much volume of rainfall was collected in the green roof. This is just length times width, but we need to convert that to meters or centimeters, depending on which way you wanna go. I think what I did for this was so the easiest way to go about these calculations is converting feet to centimeters. And there are like 30.54 centimeters in 1 foot. Can everyone see that? Am I pointing that away? Kathy, if I'm wrong on something, please call me out.
I don't think,
Okay.
I just couldn't see it.
Oh, alright. What we got? We got 43 feet times 3.54 centimeters in 1 foot. 18 feet times 13.22 centimeters. Know what y'all got? So that's just the area of the green roof, right? Next, we're gonna multiply that times, sorry, hold on. We got 1.35 inches times 30.54. centimeters in 1 inch. So 1.35, 2.54. Let's make that 3.43 centimeters. This is Am I doing better or worse than Dr. Arrow? Dr. Arrow, I had a student send me a picture. It was, what was it? It was like pound 1,000 foot squares and then like 24, 12, 16. They had no clue. They didn't know. Couldn't know. I'm like, well, that's because pound is, they're like, what is this? What is this symbol? Well, that's a hashtag for y'all. For Dr. Earhart's pound. Can't teach kids that. Did everyone come up, look? Everyone come up with this? Then we multiply it times 3.43. What do we come up with?
I'm sorry, do you have cubic centimeters? Is that, shouldn't that be
Oh, this is
square centimeters?
This is square centimeters, correct, thank you. Did I get it right over here?
No.
Nope. She is correct. Square centimeters, yes ma'am. Good eye. But we are getting the cubic centimeters right in the end, okay. So everyone clear here? Now we're just gonna multiply this big number by this little number. and that there are 1,000 cubic centimeters in 1 liter. One cubic centimeter is equal to 1 milliliter. Anybody not heard that before? Alright, sometimes it's difficult getting back and forth in between liters and metric and imperial, and it's tough for me too. Like, I really hate it because as a scientist, I'm used to dealing in liters and hectares and kilometers and all these other things, and then I have to go write an article for a local newspaper or something or other, and I gotta convert that back to pounds per acre. Right. I have to redo all my calculations. All right. In reference to the vertical farming presentations that we had, something that was mentioned, what's up, Josh?
Oh, no, I'm just doing that. I'm converted. Yeah, I'm all good.
Okay, and so we ended up having, let me go back. When we divide by 1,000 here, what do we end up getting?
2476.12.
Yep. So there would be alright. So going back to the vertical farming is one that you can capture the water from your roof and use that as your water supply. So you have decided that you want to store the rainfall from your rooftop. And we're gonna do this one in gallons, okay? Because converting that to barrels and all that stuff's a little too much. So now we don't have to do any of our centimeter conversions. When you get to your job, unless your boss tells you what you need to do that in, you do it whatever you want to. But when they tell you you need to convert it, it will be helpful to know. What do y'all want to do here first? Ma'am?
Find the area.
Okay. And in which units would you like to do that in?
Square inches.
Okay. And so what will we need to do over here?
Multiply those by 12,
Uh-huh.
and then multiply those two together.
Correct. So what she said was we will, I'm gonna wanna work in square inches, or in inches, because of this right here. Because now we have to convert this to feet. 2 ways. I'm just gonna stick with one. So she wants to multiply 21 feet times 12 inches. 18 feet. Everyone following on that? Okay? There's several different ways you can do it. You could have converted it to inches, which is a very simple way. Boom, give you the same answer. Or you could have just done square feet and then know that there are 144 square inches in 1 square foot, which makes sense, right? 12 by 12, 12 times 12, 144. I'll be honest with y'all, I looked this stuff up on Google. Like, I don't walk around knowing how many square centimeters are in a square kilometer. That stuff's on Google, there's a conversion calendar, there's a conversion calculator for that. But this makes sense to me, like I know that there's 144 square inches in 1 square foot. So, not necessarily to get hung up on the fact of knowing different areas, but that you can find this information out. All right, and then we have that times, so we have 5,432 inches squared times 0.8 inches equal to
43, 545.6.
43,
545.6.
545.6. Is that 546?
545.6. Inches.
How many square feet are in an acre? 42,560. Y'all, in all of my years of doing calculations, 13 years of school, this is the closest that I've ever gotten to an answer being close to 43,560 square feet in an acre. I was just telling some people in my lab that I've never ever gotten, that's the closest I've ever done a calculation. It came up to 42,560. That might not be cool for y'all, but it's mind blowing for me. I don't know how they came up with an acre being 43,560 square feet. They told me what it was and I memorized it and I just moved on. Closest I've ever come to calculating that answer. All right, someone figure out how many square inches, how many cubic inches are in 1 gallon of water.
Well, I looked up how many cubic inches are in a 55-gallon drum.
We can do it that way.
Then you just divide the two.
We can. All right, so she wants to do inches cubed.
Or do it in the other way.
There's 12,705 inches cubed in a 55-gallon drum.
12,705.
In a 55-gallon drum.
Yes.
How many cubic inches in a gallon of water? How much?
231.
There's 231 cubic inches. But ultimately, that's what we needed to do. We ultimately at least needed to get to 1 gallon. Or 1 55-gallon drum. So our next step would be to divide Where does this apply? Hey, I think I'm gonna go capture my rainfall. I'm gonna go to Lowe's and get a 55-gallon drum, and I'm just gonna capture everything that falls off my roof. No, you're not. You're only gonna capture 55 gallons, the rest of it's gone, right? So kind of knowing about what you're gonna get into, calculating how many drums you might need to capture the area over this, or in a green roof to know how much water is actually infiltrating that you're capturing is important. Because when you're at your job and you tell your boss that you wanna do this thing, this vertical farming, and you didn't calculate how much rainfall you were actually gonna be capturing, and you buy a 550-gallon tank, and it rains more than you use, kind of defeat the purpose, right? The goal is to capture the rainfall, not just some of it. So that's where this might come into play. And to be able to go through all this math takes a lot of time to sit down and do. But what I didn't look like an idiot in front of my boss when he came out there ready to go do his thing. And then I made an error in calculation. I've made those, they suck. They do. But when you know how to do this, they leave you alone. I don't have many people coming into my office unless they can't do the math. They're like, don't ask Natchez about math. No one asked him to do rate over analysis. Please don't. Because I turn my back and I turn into Russell Crowe from A Beautiful Mind, as y'all have just witnessed. Have you seen this before, Miss Kitty?
Yes.
Yeah.
Dr. Hart's class.
I'll make sure I post these slides so that we don't have to do a whole super bunch of this, so I can go through this a little quicker. I'm a little sick, I like doing that kind of math. And so to bring that back, what we did this for just a little small rain gauge. We did this for a green roof. We did this for like a big roof, like a building. If we can get to a 1-acre farm, then you can get to an X-acre farm. Right? So someone else has calculated the watershed. They know that you have a small portion of this. What you need to calculate is the land area that you're responsible for. Because they're not gonna come to the watershed manager, they're gonna come to yours and find out how come something is happening here, and you might need to know how much water you have. This goes for irrigation as well. You need to know how much you're gonna get and receive in acre inches, so that when you go to apply the water, you're not over applying. And you need to know how many gallons are in an acre inch, and how much water is needed, and there's gonna be some recommendations. So like, this stuff is gonna apply one day. You're gonna look back and go, oh, I remember Natchez told me this. I'll go look back at my notes. It's just area over depth. All right? So in overall watershed, they may have several stations. Does anybody have any questions about this thing they need me to go over? Did I go over that fairly simply? Was that like super redundant? Did y'all kind of know how to do that already? Sort of, maybe bring that back from high school. So we have, let's say we have a little small watershed. We have a little small watershed that has these different rain stations set up. And so there are a couple of different methods that a watershed manager might use in order to determine how much rainfall fell over their area. So there's one way, which is the arithmetic mean, which is probably something that we're all gonna do because it's very simple and very quick. We just add up all the numbers and divide, right? And so we assume that there are 2.21 inches over this 117 square mile area. Not that we're gonna go through the math, but it's 117.5 square miles times 2.21 inches, and then you'll go through that whole process again. But it's not that big a deal, because you know, if you can do a rain gauge, you can do a square roof. If you can do a square roof, you can do an acre. If you can do an acre, you can do a mile. If you can do one, you can do all of that, right? So, very simple. We have this decent.
Hopefully, it ain't gonna be that bad. I keep stuff very simple. I don't make it complicated, I hope. All right. So, for this decent polygon, we're going to connect the dots between the stations, and then we will draw lines that bisect them and basically cut them into quadrants or some section based upon equidistance. You have flashbacks? You gonna be all right? All right. So basically, you see that we've cut this into in these 5 different sections. 5, 2, 4, 5. 5 different sections. We'll overlay that over a grid that you know to be a square area, such as a mile. So each one of these blocks is a square mile. You'll overlay that and calculate how many blocks you filled up in that one area. So over here on the left, again, like I said, I will post these notes. So I did most of the work. These are the areas in square miles for each one of those little polygons. And that's how come I knew that there were 117.5 square miles in this watershed. You will